So far we have been considering single degree freedom systems which did consist of only one of each element, that means one block representing the inertia, that is the mass, one spring which represented the restoration. However, there can be single degree freedom systems which consists of multiple number of bodies representing inertia, multiple number of springs of different types representing the whole effort that brings the system to its equilibrium, that is restoration. So, in such cases the technique to solve the problem will be to convert the whole system into a simple spring mass system, but which is dynamically equivalent to the original system. So, therefore, in this lecture we will take up the discussion on techniques for finding out the equivalent inertia and equivalent stiffness. So, we have a system, the actual system, and we convert into an equivalent system. But when you do that, it must be dynamically equivalent. Dynamically equivalent means that if I apply certain force or certain moment, the acceleration produced in the system will be same as that what would have happened if the same force or moment had been applied to the actual system. Now, how do you find out that? How do you ensure that? Now, of course, since a system has to be dynamically equivalent, we must always keep in mind that they have to be kinematically equivalent also. That means the velocities, displacements and accelerations of the various points or members in the original system must be same all the time as that in the equivalent system. Now, to find out how we can do that, so let us consider this, that this is the equivalent system. So, let this equivalent system be an inertial mass M equivalent. Now, M equivalent we have chosen in such a way that if its speed or velocity, whatever it may be, at this instant be v, then this kinetic energy is equal to the kinetic energy of the actual system. Now, if we apply a force, we know that force, when it works through a small infinitesimal distance dx, is the amount of work done. Where that work will go, that energy will go to increase the kinetic energy. If we consider that the potential energy remains same, then this will be nothing but change in the kinetic energy, if we assume that potential energy remains same. So, if we divide this by dt, then we get F into V will be equal to ddt of kinetic energy. Now kinetic energy is same as this, so this will be nothing but M equivalent into V into A, which is dA dV dt. This is A is nothing but acceleration. Since V is not 0, so from this we get that F by M equivalent is equal to the acceleration. So we produce the same acceleration by applying the same force if the mass we choose is such that its total energy or its energy for a same velocity is identical with that of the original system. So therefore, the technique of finding out the equivalence is keeping the total kinetic energy of the actual system and representing that by a single mass M equivalent in this form. Similarly, without going into details, we can also tell that for finding out equivalent restoration or equivalent stiffness, we will find that giving the same deflection to a particular point where a force is applied, the total amount of strain energy in the system will be same as that of the equivalent system. So if we take up some simple cases, let us take up first a case where we have so there is one mass M connected by a linear spring K to a fixed wall, and at one portion of the lower edge or lower surface of this mass there is gear, it is like a rack, and that is in engagement with a gear or a wheel, a part of which is having this teeth. The radius of this disc may be r, and its moment of inertia is I, about an axis passing through O. Further to this disc is connected to a fixed wall with the help of a torsional spring whose stiffness is capital Q. Thus, the system consists of two bodies which possess inertia. One is moving in a linear direction, that means which is having displacement x, and another object which is having a rotation correspondingly, rotation theta. This has a mass m and it is connected by a linear spring to a solid wall, and this disc whose moment of inertia is I because it can rotate about this, it has a radius r, and it is connected to the foundation by a torsional spring K. Now, and its displacement is indicated by a rotation theta. Now, this theta and x are obviously not independent, because it is a single degree freedom system. Any one quantity you specify, it should completely specify the configuration of the system. So either you mention theta or you mention x, and they are related by this. X is nothing but r theta. So from their equilibrium position, if we give a displacement x to mass m, the disk automatically rotates by an angle theta due to this gearing action here, which is related by this relation. So it is a single degree freedom system, though it has two bodies. Now, if we want to find out an equivalent, we can find out two types of equivalent system. We may consider x displacement to be the primary thing. So it's a simple spring mass system with a mass m equivalent and the connection to the wall by another equivalent spring whose stiffness is A equivalent. But the displacement parameters will remain same as the original body, because its kinematics must be same. Now you may say, or one may say, why you take up that as the primary body? We can take a rotation and we can represent the equivalent system to be a rotating system. Connected by a torsional spring capital K equivalent, and the moment of inertia of this is I equivalent. Of course, its angular displacement will be from the equilibrium position will be represented. Both are possible. That means equivalence can be either this, it is purely our choice. Now, what will be these values of M equivalent and K equivalent? As I mentioned that the equivalence is determined in case of mass by the total kinetic energy of the system and the kinetic energy of the equivalent system, which should be same. What is the kinetic energy of the original system? First is linear kinetic energy of this, half m x dot square, and angular velocity of this is theta dot. Therefore, x dot is equal to r theta dot. So it will be half I theta dot, which is same as half m plus theta dot is x dot by r. So you can write this by I or we could write as half m x dot is r theta dot both are possible. Similarly, potential energy for any displacement. Now there is no gravitational potential energy involved because this disk is remaining at the same location, though it is rotating, so its potential energy due to gravity is not changing. This mass also is, center of mass is not changing any level because we have placed it in a horizontal guide. Therefore, the potential energy due to gravity of that mass also remains constant, and we can treat the potential energy and the equilibrium position to be 0 at it remains 0 all the time. But strain energy in the two springs, this linear spring and torsional spring, will provide the potential energy. So the distortion or stretch of this spring from its equilibrium position is x, and the equilibrium position it was under no strain condition. So therefore the linear spring's strain energy is half kx square. Similarly, This also we consider that during or at the equilibrium position, this particular torsional spring was also torque free, and the potential energy stored or the strain energy stored in the torsional spring will be this. Now, using this relation, we can write it like this: half K plus, now theta is equal to x by r, so it will be capital K by r square, or you can also write this as half K and x is equal to r theta So, the kinetic energy we will use for determination of the M equivalent and potential energy we will use for finding out the K equivalent. That means, if we say that let us use two different colors, one for this, one for this. So, I will say that since we have taken an equivalent system to be a linear movement, so we will take up this. So, therefore, this should be equal to half M equivalent into dot square. That is the kinetic energy of the equivalent system with the same velocity, of course, that you have to always keep in mind. So, we get M equivalent as now K equivalent, this is equal to half K equivalent x square. So, therefore, we get K equivalent is equal to and what will be the equation of motion for this? M equivalent x2 dot plus K equivalent x equal to 0 and omega n will be equal to square root of K equivalent by M equivalent. Or simply now, if we try to solve the problem by considering an equivalent system which is executing angular motion, then let us use this. So, then we will take this, therefore, its equivalent total kinetic energy is half I eq theta dot square, and equating these two we get similarly its total potential energy is half or K equivalent is nothing but and the equation of motion of this is nothing but I equivalent theta 2 dot plus K equivalent theta. This is coming directly from Newton's second law. The total torque acting on this when it is under angular displacement theta is K equivalent into theta, and that must be equal to I equivalent into theta 2 dot by Newton's second law. So, this is nothing but the and obviously omega n will become equal to K equivalent by I equivalent. the same result you get. It cannot be different so far as the frequency is concerned. So thus we have seen that the system, when it is complicated, it is always desirable to model it in the form of either a simple spring mass system or a simple disk torsional spring system, and then determine the equivalent mass and equivalent stiffness by equating the kinetic energy of the original system with the kinetic energy of the equivalent system, and so on. Next thing what we have to also see, that sometimes the elements like the restoration elements like springs, they may be combined. That means we may not have a single spring like this, or here you find a single torsional spring, a single linear spring. Sometimes a composite structure may be there which consists of a number of elastic bodies, and in such cases the resultant stiffness of the spring or the restoring element has to be found. Next, let us consider the case of a composite spring system and how we can find out the equivalent system, which can be represented by either a simple linear spring or torsional spring. So first let us consider the springs in series. So the simplest composite system will be two springs of stiffnesses K1 and K2 respectively are connected in series. Our job is to find out that what will be that equivalent system. Now we have to find out the equivalence. What should be the condition of the equivalence? As we mentioned, that the energy stored in the system here, energy stored in the system here should be same, or in other words we can also tell that the deflection caused here under this force should be same as the deflection caused here. So we will not understand the difference whether there are two springs or three springs. We will find that we are applying a force and it is causing a displacement delta. Same thing here, we are applying a force causing a deflection delta. So therefore we treat that these stiffnesses are identical. Now what will be the, here the stiffnesses are known. Let us find out that under the action of the force, what is this deflection. It is very clear to see that this displacement from this original position is nothing but the stretch of this spring plus stretch of the other second spring. So what is the force transmitted or sustained by these two springs? It is the same force F, because if you draw the free body diagram, it's quite trivial, but just so the force acting on the second spring is F, and the same force is acting on the first spring. So therefore the stiffness of this is K1, stiffness of this is K2. So the amount of stretch in this will be nothing but F by K1, and the amount of stretch in the second spring will be F by K2, and since they are in series, the total stretch will be sum total of this, which should be same as that equivalent spring whose amount of stretch will be under the same force equal, which is delta. So we find that 1 by K equivalent is equal to sum total of 1 by Ki, I is equal to 1. If there are n number of springs connected in series with stiffnesses K1, K2, K3 up to Kn, then the relation between the equivalent stiffness of a single spring which will produce the same degree of elasticity or stiffness is given by a simple relation. Now, the other possible case, that is when springs are in parallel. Again we will consider case of two springs which are now in parallel and subjected to a force F. We have to find out an equivalent stiffness for a simple spring which can represent the stiffness of the original system. That means again we will find out that the deflection of this point under the action of this force F will be delta, which should be same as the deflection of this point under the action of the same force will be equal to the same as delta. Now, here you will find, if you draw the free body diagram, now you find that this spring is, suppose for example, subjected to a force F1 and this one is subjected to a force F2 and this point, this is subjected to F, this side F1 and this is of course massless and no resistance. So therefore, one thing is very clear, that F is nothing but F1 plus F2. And how much is F1? Now, both the springs have undergone same amount of stretch, which is delta. So therefore, the force in this will be K1 into delta, force in this will be K2 into delta. So therefore, this is nothing but K1 into delta plus K2 into delta. We can take delta outside. We also know that this force is same as K equivalent into delta. So therefore, when the springs are in parallel, K equivalent is nothing but sum total of the stiffnesses. So this is the basic rule. Now a real system, there may be still more complicated systems, some are in parallel, some are in series, all these things, but I think one can understand that following these two rules, any kind of complex system can be found out or can be handled and can be represented by a simple spring. Now, of course, we have shown it in the case of linear springs. In torsional spring situation also, the system can be found out and equivalent stiffness can be found out. Now, this energy technique which we have been discussing can be used also to solve certain other types of situations which cannot be handled by simple Newtonian approach. So, one such example is, which is perhaps appropriate to discuss at this juncture, is if a system has heavy springs and it is desired that the mass of the spring is also considered, at least approximately. So, how we can find out the natural frequency of such system? because though we have mentioned earlier that while solving problem we always lump the parameters, and what we are actually handling is a lump parameter system. But while lumping, we thought originally in the simple cases that the springs are very light and they may be considered massless. The block is the only thing whose stiffness is extremely high and it can be considered to be rigid, and that represents the inertia only. But there can be situations where it is desirable to consider the spring mass, and we will solve that problem. So this is our system now. That means it is a simple spring mass system. The block has a mass m which oscillates freely in the horizontal direction. The spring has a stiffness k and a length or a mass ms, and the length of the spring is L. So now we have given the mass of the spring ms, and we want to find out the natural frequency of the system. So therefore what we will do, as we have been thinking all the time, that we will have to have a lump parameter system. We will solve that system where this spring has been replaced by another spring whose stiffness is same k, but which is massless, and the effect of the spring mass has been taken care of by the equivalent inertia. And we will obviously use the same technique as before. We have already seen that the equivalent inertia is found out by considering the total kinetic energy of the replaced system or the equivalent system to be same as the total kinetic energy of the original or the actual system under the same kinematic conditions, that is the same velocity. So here also the equilibrium position is the same. And now let us consider this one. When it deforms, and the original equilibrium position is this, and the displacement at this instant under consideration is x. Its velocity, of course, also x dot in this direction algebraically. Let us find out under this condition what is the total kinetic energy of this. Now total kinetic energy of this is obviously first the kinetic energy due to the block, which is half m into velocity of the block is x dot in that square. Now how much is the kinetic energy stored in this or the spring? Now that we have to find out by considering each element of this spring. Let us consider an element at a distance zeta from the fixed end, whose length is d zeta. So that particular element has some mass, and the point is, what is the velocity of this element? That velocity is how much? Here what we can do, we will do this. We will assume that the formation of the spring is linear. This is an assumption, though it is not very different from the actual case, but exactly it is not so. But we assume that at the fixed end of the spring, the displacement is 0, and when it comes here, obviously the displacement is x. Similarly, velocity also will be proportional. So velocity at this end is x dot, velocity at this end is 0. So velocity at zeta will be how much? It will be x dot into zeta by L, if you have taken a linear distribution of. So what we can do, we add the kinetic energy of the spring. First, the element, the mass of the element is d xi by L into ms. That is the mass of the element. Mass per unit length of the element is ms by L, and the length of the element is d xi or d zeta. So d zeta ms by L is the mass of this thing. What is the velocity of this element? We have found out x dot into zeta by L. So the square of that. So this is the kinetic energy of the element. So the kinetic energy of the whole thing will be sum total of the kinetic energy of all the elements. That means we can just integrate. How much is that? This is half mx dot square plus half this ms and by L cube goes inside, outside, and integration of x dot also goes here, x dot square. Now zeta square d zeta integration is zeta cube by 3, and putting the limits, you get this. It is same as half m plus ms by 3 x dot. So this is the total kinetic energy of the original system, and kinetic energy of this is half and that must be equal to the kinetic energy of the original system, and thus we get m equivalent is equal to m plus ms by 3. Now we must remember that this relationship which we have got actually is slightly approximate, because this approximation that we consider that the displacement of each element is linearly proportional to its distance from the fixed end, which is not exactly correct, but the error introduced is very small. So everywhere there is certain degree of approximation involved, and therefore we find that taking care of the spring mass is pretty simple. Only thing what you have to do, you have to add 1/3 of the spring mass to the mass of the block, and therefore natural frequency can be easily found out from this. So you have seen that energy technique or energy approach can really help us in solving many problems which may not be that convenient to be taken care of using direct Newtonian approach. Next one thing which we will take up in today's lecture is representation of this harmonic oscillation in a particular way which is called phase plane representation. The phase plane representation sometimes can be very convenient in solving certain problems, and I think it will be appropriate to introduce this particular topic at this juncture, and whenever the application will come in future, we will just remember the discussions here and apply the technique and the concepts which we are discussing. If a spring mass system, say for example, a simple spring mass system, the mass is executing harmonic oscillation. It can be angular oscillation also. The equations are same or similar. Now, for all small oscillations, we know that we can represent x by a harmonic function. This we have used even while considering the energy approach. So, the harmonic oscillation of this object is being represented by this function of time. So, we know x dot will be then that is instantaneous speed of object will be this, or a quantity if we define the velocity, instantaneous velocity divided by its natural frequency, it will be and if we square the displacement and square the instantaneous velocity divided by natural frequency, circular natural frequency, square them, then obviously we get constant. So, if we plot instantaneous displacements and instantaneous velocity by natural frequency, which is constant for the system, then obviously we will get a circle, because this is nothing but the equation of a circle. So, therefore, this plane which we are constructing is not the physical plane, because one axis represents the velocity and the other axis of course represents displacement. So, this plane is not a physical plane, this plane is called the phase plane. Why phase plane? Because at every point here identifies what is the position and what is the speed, that means the phase or the state of motion of the system. That is why it is called a phase plane. And here a harmonic oscillator, the points representing its state of motion will describe a circle with this as the amplitude. So, displacement at any instant is nothing but x sine omega n t, if we consider this to be the 0 position, and this is nothing but x which happens to be velocity divided by omega n. And of course, the phase plane diagram for a simple harmonic oscillator is a circle whose radius is the amplitude, and one thing should not be forgotten, that means there is an arrow. This arrow has to be in this way, because when velocity is in the positive quadrant, this here, so when velocity is positive, x dot is positive, algebraically x must increase. So during this half cycle, x is increasing because velocity is positive. On this side where velocity is negative, x is decreasing from this value to this. That is why the arrowheads are unique, and it must be represented like this. Now this concept that the representation of a harmonic oscillation can be made with the help of a circle in the phase plane is a very useful concept, mainly because circles can be drawn very quickly and conveniently. It has other use also. For example, let us take a simple example. Let a system a 5 kilogram mass and this is a 125 Newton per meter, just a hypothetical case, is the stiffness. So it is taken Let us say simple problem. There is a mass 5 kg connected to a spring which is again connected to a fixed wall. Stiffness is 125 Newton per meter. Then the mass is pulled to a position in this direction by 0.1 meter and then pushed with a speed 2.5 meter per second in the positive x direction. Determine the amplitude of resulting oscillation. Now we can solve the problem by other approach also, but the objective here is to the use of phase plane diagram. So the state point, if we can find a single point which represents the state of motion of the object our job is done. Wherever the point is, the ensuing motion will have to be a circle with O as the center. Say for example, therefore, what is x? X is say 0.1. And what is this? The speed x dot by omega n. Now omega n we can find out, omega n is equal to square root of 125 by 5 equal to 5 radian per second. So x dot in meter per second divided by 5 radian per second will give you simply meter. It is same, so therefore you have to use the meter per second. So here 2.5 by 5 is how much? 0.5. So amplitude of motion, the ensuing motion is going to be a circle starting from this is the starting point where the displacement is 0.1 and x dot by omega n, x dot is 2.5 meter per second, omega n is 5, 2.5 which is 0.5. So therefore this is the starting point and it will describe a circle from there. So x will be equal to square root of 0.01 plus 0.25, so many meters, 0.5. So this problem can be solved so quickly using the technique of phase plane without even solving an equation. So more use of phase plane technique will be coming in the future, and we will take up the problems when it comes.